What if I told you that giving a large language model a complement on its code is statistically identical to giving it absolutely zero feedback at all?
Yeah, literally a wasted token.
Right. Welcome to AI Paperslap. Today we are looking at OpenDeepThink, parallel reasoning via Bradley-Terry aggregation. This is new work from Shang Zhu and a team of researchers from UC San Diego, Princeton, UW, and UC Berkeley.
It's a really heavy-hitting lineup.
Totally. And for you ML engineers and AI researchers tuning in who are, actively working on inference scaling, here is the 30 to 60-second blitz.
Let's do it.
So we know test-time compute scaling is currently bottlenecked by sequential reasoning. Basically, if you just extend a single chain of thought, one early misstep just derails the whole trace, right?
Right, the whole thing falls apart.
Exactly. So parallelizing through best-of-n sampling seems like the obvious fix. But it's incredibly hard to implement without a ground truth verifier because point-wise LLM judging is noisy and overwhelmingly positively biased.
Which means the model basically just rubber stamps bad code.
Yeah, it just says good job to everything.
Yeah.
So OpenDeepThink introduces this verifier-free, population-based framework to fix it. It forces candidate solutions into pairwise LLM battles, aggregates the win rates using a Bradley-Terry model, and then mutates the code based purely on the negative critiques generated during those battles.
And the results on this are just wild.
Unbelievable, honestly. The headline result is that it boosted Gemini 3.1 Pro's effective code forces ELO by plus 405 points in just 8 sequential LLM calls.
Wow.
Yeah. Which is about, 27 minutes of wall clock time? And it accomplishes all of this without needing any hidden test cases or compiler feedback.
See, the top-line ELO boost is definitely what grabs the attention. But, the underlying mechanics of how they actually bypass the selection bottleneck is what makes this a truly significant paper.
Oh, for sure.
We really have to look at why scaling test-time compute horizontally, meaning, generating a broad parallel pool of candidate solutions, why that has historically been so much harder than scaling vertically by just prompting a model to think longer.
Right, because horizontal scaling relies on the judge.
Exactly. The core culprit is the judge. So to really appreciate the elegant solution in OpenDeepThink, we have to dissect why existing parallel selection methods just completely fall apart the second you remove a trained reward model.
Let's start with the current meta then. Like, if you don't have a verifier, the standard approach is self-refinement, right?
Right, you see this all the time.
Yeah, in methods like self-refine or reflection, you generate a single trajectory, look at it, and ask the model to fix its own errors. But the paper points out that this suffers from a phenomenon they call the cognitive well.
I love that term. The cognitive well is just a great descriptor.
It really paints a picture.
Because a single trace struggles immensely to identify its own structural or logical errors. The model gets stuck in this local minimum where it patches a flawed approach.
Like just changing a variable name or something?
Yeah, tweaking a variable name or adjusting a loop condition instead of fundamentally revising the underlying algorithm. It was essentially hill climbing on a broken initialization.
So you're just polishing a turd, basically.
Basically, yeah.
So the natural pivot is to generate multiple different solutions, say 20 parallel candidates in a best-of-n setup.
But then you hit a wall.
Right. The problem there is you suddenly have a selection bottleneck. How do you pick the winning trace? If you are generating C++ for a competition, but you don't have a compiler hooked up to run hidden test cases, you have to ask an LLM to grade the candidates.
Which is rough.
Yeah. You hand it one piece of code and ask, score this from 1 to 10, or is this logic correct? That is point-wise judging.
And this is exactly where the entire pipeline usually collapses. LLMs are terrible at objective, isolated evaluation.
The data point they provide on this completely reframed how I look at LLM evaluation. They ran a diagnostic using the NOI 119 benchmark. Point-wise judging achieved 96.4% accuracy on identifying solutions that were actually accepted.
So it recognizes working code almost perfectly.
Right. But on wrong answer solutions, the accuracy plummets to 62.2%.
That is a massive drop. The model fundamentally resists rejecting incorrect candidates. It has this huge false positive rate.
I'm trying to picture why that happens mechanically. Is it basically that one teacher who gives everyone an A for effort? Like if you handed a structurally flawed Python script, it seems like the model actively searches for reasons to praise the code.
That's a perfect analogy.
Like maybe the syntax is clean or the variable naming conventions are standard, so it just signs off on the whole thing and ignores the broken logic.
Yeah, and that behavior likely stems from the instruction tuning phase of most modern models.
Oh, because they're trained to be helpful.
Exactly. They're heavily optimized to be helpful and agreeable. So when you present an isolated piece of text and ask for an evaluation, the model defaults to a generative mindset rather than a strict discriminative one.
It's just trying to be nice.
Pretty much. It looks for the positive signals. However, the dynamics change completely when you move to a comparative task. And the diagnostic data in the paper illustrates this beautifully.
Right.
They took a 500-pair diagnostic data set and evaluated pointwise judgments against pairwise judgments.
So pointwise is looking at them in a vacuum, and pairwise is putting them side by side.
Correct. The pointwise approach hovered at a dismal 59% overall accuracy. But pairwise judgment, using the exact same judge model, just asking which of these two is better, it hit 86% accuracy.
Wow.
Yeah. They even randomized the presentation order to prevent the model from always favoring the first option, which is a known position bias. But the delta is undeniable.
It makes intuitive sense, right? Like spotting the flaws in a bad essay is so much easier when it's sitting directly next to a masterpiece.
Yes, the contrast creates the signal.
Yeah, it simplifies the cognitive load on the model. Instead of maintaining this complex abstract standard of perfect code in its latent space, it simply has to identify relative weaknesses between A and B.
Exactly. It's much easier to spot a flaw when you see how someone else avoided it.
All right, I buy that. Pairwise comparison is the superior signal. But if I put on my ML engineer hat for a second, my immediate concern is combinatorial explosion.
The dreaded n squared.
Yeah. If I have a population of, say, 100 candidate solutions, comparing every single pair means n squared comparisons. That is 10,000 LLM calls just for one step of evaluation.
Which is absurd.
Nobody has the API budget for that. So how does OpenDeepThink extract that clean pairwise signal without bankrupting the whole project?
Well, they avoid the n-squared trap by heavily constraining the evaluation graph.
Yeah.
The authors introduce a very specific set of hyperparameters to control the cost.
Okay, lay them on me.
So the population size n is capped at 20. But the real trick is the comparison parameter, k. For each generation, a candidate is only compared against k equals 4 random peers, not the entire pool of 19 other solutions.
Oh, interesting.
Yeah, and the whole evolutionary loop only runs for t equals 3 generations.
I want to break down exactly what happens in one of those generations. Because step one is the compare step, right? We have our 20 candidates, and each one gets thrown into 4 random head-to-head battles.
Right. In that compare step, the LLM looks at the random pair and outputs a JSON. It is prompted to declare which solution is more likely to be accepted by an online judge or to declare a tie.
Okay.
But the crucial structural requirement is that the prompt forces the LLM to write a brief, one-sentence natural language critique for each side before declaring the winner.
And we are definitely going to come back to those critiques because I know they do a lot of heavy lifting later on, but I'm still hung up on the math of the ranking here.
What do you mean?
Well, if a candidate only faces 4 random opponents, the raw win rate is going to be incredibly noisy. Like winning 4 battles against the absolute worst code in the pool doesn't make you the best overall.
Oh, absolutely. That is the exact limitation of a raw win rate metric. It completely ignores opponent strength. And to solve this, the framework uses Bradley-Terry aggregation.
Now, for listeners who might not be deep into ranking theory, Bradley-Terry is essentially the algorithm that powers Chatbot Arena, right? Like when you blind test 2 LLMs and vote for the better one, Chatbot Arena uses Bradley-Terry to figure out the global leaderboard.
That is a brilliant analogy.
Yeah.
Bradley-Terry is a probabilistic model that assumes every item has a hidden latent strength score. The probability of candidate A beating candidate B is just a function of the difference between their strength scores.
Okay, so it's all relative.
Exactly. But because we only have sparse data, just 4 random matchups per candidate, we have to estimate what those hidden strength scores actually are.
And the paper mentions they use LBFGS to do that estimation. I know it's an optimization algorithm, but how does it actually translate those sparse matchups into a global leaderboard?
Think of LBFGS, which stands for Limited Memory, Broyden, Fletcher, Goldfarb, Chenot. By the way, think of it as a highly efficient landscape navigator.
That's a mouthful.
Yeah, it really is. But basically, you give it the chaotic web of wins, losses, and ties from the compare step. The algorithm iteratively tweaks the hypothetical strength scores of all 20 candidates, trying to find the exact configuration of scores that makes the observed match outcomes most probable.
Oh, I see.
Yeah, it internalizes the strength of the opponents mathematically, distilling those sparse, noisy battles into a coherent 1D global ranking.
That is so clever. So they essentially built a micro chatbot arena inside the inference loop for a single coding problem.
That's exactly what it is.
They have a fully functioning soft verifier that requires zero labeled data. Okay, so once LBFGS spits out the ranked leaderboard, what happens to the candidates?
The population is split based on those rankings. The top 25% of the population are classified as elites. The bottom 25% are discarded completely. They are just assumed to be evolutionary dead ends.
Makes sense.
And then the top 75%, which notably includes those elites we just mentioned, are moved into the mutation phase.
Wait, I have to challenge the logic of mutating the top 25%.
Go for it.
If the elites are already dominating the microarena, why mess with them? Like, by mutating our absolute best code, aren't we risking breaking the only working solution we might have actually found?
That would be true if the framework operated on strict replacement, but it doesn't. It uses elite preservation.
Okay, how does that work?
The original version of an elite candidate is safely carried forward to the next generation completely untouched. It is banked.
Ah.
However, it also serves as a seed for a mutated variant, so you guarantee that your capability ceiling never drops. You never lose your best-known solution, but you still apply immense evolutionary pressure to see if that elite solution can be pushed even further.
You lock in the win, but you still roll the dice on a parallel track.
Exactly.
That makes total sense. Let's move into the mutation phase itself, because this touches on what I think is the most fascinating behavioral quirk highlighted in the paper.
Oh, the feedback ablation.
Yes. We've dropped the losers, we've banked the elites, and now we have to rewrite the middle of the pack and the elite variants. What are we actually telling the LLM to do differently?
To answer that, we have to look at the ablation study they ran on feedback strategies, which is detailed in Table 3 of the paper. The researchers tested multiple ways of prompting the mutator model.
Right.
The baseline scenario was providing no feedback at all, just showing the model the code and asking it to try again. That baseline yielded a 47.6% accepted rate.
And then they tried positive feedback. They fed the model the code, told it what it did correctly in the previous generation, and asked it to refine it, and the result was a 47.8% accepted rate.
Yeah. The statistical delta between positive feedback and total silence is essentially zero.
I find that endlessly interesting. Like, we spend so much time crafting prompts to encourage LLMs, but mathematically, telling the mutator what went right adds absolutely nothing beyond what the model already infers just by reading its own code. It is literally a wasted token.
It really highlights a limitation in how models process self-affirmation.
How so?
If you tell an LLM its logic is sound, it becomes complacent. It doesn't explore new algorithmic pathways. However, when they switched the prompt to purely negative feedback, shoving its head-to-head losses in its face, the acceptance rate pushed to 49.4%.
Wow.
It is essentially a form of adversarial self-improvement.
But the optimal strategy was providing aggregated pairwise feedback across all k=4 opponents, right?
That's right.
That strategy yielded the best rescue rate of 52.4%. That is a plus 68 delta in rescuing wrong answer solutions into accepted solutions compared to the baseline.
And the efficiency of this is what really stands out to me. The critiques required for this optimal feedback strategy are actually a free byproduct of the compare step we discussed earlier.
Right, the JSON output.
Exactly. Remember the JSON.
Here.
They aren't spending extra API calls or adding latency overhead to generate this feedback. They simply parse the JSON from the Bradley-Terry ranking phase, group the critiques by wins, ties, and losses, and inject that compiled dossier directly into the mutation prompt.
So the model is basically reading the judge's notes from its own trial.
Yes.
And the wording of that mutation prompt is doing some critical behavioral work too, specifically what they call the license to abandon.
This is such a smart addition. The prompt explicitly instructs the mutator. You may refine the existing solution or take a different approach if the current one is fundamentally flawed.
Which seems like a really minor semantic detail, but it directly attacks the cognitive, what we talked about at the very beginning.
It is a vital escape hatch. Without that explicit permission, LLMs default to local hill climbing. They will stubbornly try to tweak a broken algorithm because they assume the initialization must be preserved.
They don't want to throw away their hard work.
Right. But by explicitly granting the license to restart, the mutation step allows the model to traverse to qualitatively different solution sketches. It breaks the local minimum.
So the theoretical engine is highly cohesive. You generate a pool, force them into pairwise battles, rank them with Bradley-Terry and LBFGS, cull the bottom quartile, mutate the survivors using free negative feedback and a license to abandon, and repeat for 3 generations.
It's an elegant pipeline.
It really is. But let's look at the operational reality. Because ML engineers deploying this at scale need to know the actual cost and where this framework provides the most marginal value.
Right. The compute budget is significant, but it's highly structured. The total cost is approximately 285 API calls per problem.
Honestly, 285 calls for a single coding problem sounds prohibitively expensive for a production environment.
It sounds high if you equate API calls with latency. But we have to look at the sequential depth of those calls. The entire pipeline is exactly 8 steps deep.
Walk me through the math there.
Okay, so you have the initial sampling of 20 candidates, which is one sequential step because they generate in parallel. You run 3 rounds of evolution, and each round has a compare step and a mutate step that's 6 sequential steps.
Okay, so we're at 7.
Right, and finally you have one dense selection round at the very end, which is 1 step. 1 plus 6 plus 1 equals 8.
Okay, so because all the generations and judgments within a specific step are embarrassingly parallel, your wall clock time is just 8 times your API latency.
Exactly.
The paper notes a roughly 200 second per call latency for Gemini 3.1 Pro when dealing with complex competitive programming traces. So you are looking at about 27 minutes of wall clock time.
27 minutes to crack an extremely difficult competitive programming problem without a compiler is a remarkable trade-off for inference compute.
It really is.
And to understand where that compute is best spent, we really have to examine the difficulty tiers. The researchers stratified the benchmarks CF73 and NOI 119 into easy, medium, and hard tiers based on the base model's zero-shot capabilities.
And pass at 1 is the metric they use here. For anyone unfamiliar, pass at 1 just means if you generate exactly one answer, what are the mathematical odds it's completely correct?
Right. So on the easy tier, the random pass at 1 rate of an unranked sample was already 100%. The base model solved it perfectly on the first try.
Oh, wow.
Yeah, in those scenarios, the entire OpenDeepThink evolution pipeline does literally nothing.
So the capability is saturated from the jump. You are just burning tokens for the sake of it on the easy stuff.
Exactly. But the narrative shifts entirely on the hard tier. On those problems, the random pass at 1 starts at a mere 11%.
A huge difference.
Huge. And over the 3 generations of evolution, the raw capability of the candidate pool climbs to 36%. The evolutionary pressure is actively generating better CADE.
That's awesome.
Then, the dense Bradley-Terry top 1 selection kicks in. In this final step, M equals 10, meaning each surviving candidate is compared against 10 peers instead of just 4. That dense verification extracts the absolute best trace out of the evolved pool, pushing the final success rate to 50%.
Okay, let me play devil's advocate regarding the budget for a second.
Sure.
If I have a massive inference budget, why wouldn't I just run best of 10,000? Like if I blindly throw enough parallel tokens at the wall, won't I eventually generate the correct answer and find it?
You might generate the correct answer, but finding it is the problem. The larger your uncurated pool, the harder the selection task becomes. The authors run an ablation on the budget that addresses this directly.
Oh, really?
Yeah. Figure 3 maps out the efficient frontier between population size, which is N, and comparison rounds, which is M. If you are constrained to a budget of exactly 120 calls, the mathematically optimal configuration is a population of 20 and 10 pairwise rounds.
So going wider introduces too much noise and going deeper wastes tokens.
Precisely. If you expand the population to 50, you generate more candidates, but you don't have enough budget left for the dense pairwise comparisons needed to accurately rank them. The noise overwhelms the signal. But if you shrink the population to 5 and do massive amounts of comparisons, you have extreme confidence in the ranking. But the pool is too small to contain a highly evolved variant, so N equals 20 and M equals 10 strikes the perfect balance between diversity and verification.
Which brings us to the results. We mentioned the plus 405 ELO Boost on code forces for Gemini 3.1 Pro earlier, but the paper notes they use a maximum a posteriori estimation under a Gaussian prior to calculate that?
Yeah, the MAP estimation is a rigorous way to prevent a single lucky submission from wildly skewing a model's rating. Instead of jumping to conclusions based on one lucky win, the Gaussian prior anchors the model's ELO.
It makes it earn it.
Exactly. It requires sustained, consistent performance against known problem difficulties to pull the rating up. A plus 405 shift under MAP estimation is massive. It is comparable to the capability jump between an entire generation of foundational models.
That's crazy, but does this framework transfer, like if it only works on Gemini 3.1 Pro for competitive programming, it's a neat parlor trick, but it's not a generalizable pipeline.
The cross-model transferability is actually heavily validated. They took the exact same hyperparameters, n equals 20, k equals 4, t equals 3, m equals 10, and applied them to Gemini 3 Flash and Gemini 2.5 Pro without any retuning.
And it worked.
The gains were massive across the board. However, the internal dynamics shifted based on the base model's capability.
Meaning the weaker models relied on different parts of the pipeline than the stronger models.
Precisely. For Gemini 3 Flash, the weakest model tested, the biggest performance lift came in the base generation rate. The mutation and evolution phases were doing the heavy lifting to slowly piece together competent code.
Makes sense. What about Pro?
For Gemini 3.1 Pro, the candidates were mostly competent from the start, so the biggest lift came from the final dense Bradley-Terry selection, accurately identifying the winner. The framework dynamically reallocates its utility based on what the base model needs most.
That adaptability is incredible. But my main point of confusion is the domain transfer. They ran OpenDeepThink on HLE Humanities' last exam, which is a brutal benchmark covering everything from quantum physics to literature.
It is notoriously hard.
Right. And on the objective domains like math, physics, and biology, the pipeline added up to 17 points of performance. But on the subjective domains, humanities and social sciences, the performance dropped by almost 30 points.
Yeah, that was a wild finding.
If the evolutionary engine is so robust, why does it actively mutate a humanities answer into something 30 points worse?
This exposes the fundamental boundary of the LLM-as-a-judge architecture. The entire evolutionary soft verifier relies on the assumption that the pairwise comparisons are tethered to some objective reality.
Okay.
In math or code, the judge can objectively identify a logic flaw or a boundary condition error and declare a clear winner.
The signal is anchored in truth.
Yes, but in the subjective humanities debate, or like advanced poetry analysis, there is no objective truth for the model to latch onto. The judge's preferences become arbitrary, heavily biased toward stylistic quirks, formatting, or length.
So if the judge is essentially hallucinating a preference based on style, the Bradley-Terry aggregation isn't distilling a clean signal, it is mathematically amplifying the noise.
Exactly. The iterative selection sends the population down an evolutionary dead end. The mutator starts optimizing the answers to satisfy the idiosyncratic stylistic preferences of the judge model rather than aiming for factual or analytical correctness.
That's a huge blind spot.
It is a vital caveat for anyone looking to implement this in general-purpose agents. The pipeline demands objective verifiability to function.
Which is why the researchers were so careful with their primary dataset, right? For anyone wanting to test this on their own hardware, the authors released CF73.
Right, a great contribution to the community.
It is a curated set of 73 code forces problems post-dating August 2025. They were expert-rated by an international grandmaster and showed 99% agreement with the official code forces verdicts. It guarantees you aren't just measuring pre-training memorization.
The rigor of CF73 really solves the data contamination issue that clouds so much of the current literature on reasoning models.
Okay, let's pull all of this together. If you are building agentic workflows or trying to scale inference compute without relying on a compiler, OpenDeepThink is a blueprint.
Absolutely.
By structuring parallel generation into pairwise battles, using Bradley-Terry aggregation to filter the noise, and mutating the survivors purely on their negative critiques, you can extract a massive capability jump in just 8 sequential API calls.
It transitions the field from vertical chain of thought scaling into horizontal evolutionary scaling. But, it leaves us with a fascinating theoretical boundary to consider.
Oh, what's that?
If this entire framework relies completely on the base model's ability to accurately judge head-to-head matchups, what happens to test-time compute scaling when the generator model becomes so advanced that it writes code or mathematical proofs that are simply too complex for its own judge counterpart to comprehend?
That's a scary thought.
When the solver outgrows the critic, does evolution stop?
That is the ultimate bottleneck. If the judge can't comprehend the genius of a highly mutated trace, it might throw away a groundbreaking algorithm just because it prefers a simpler, albeit wrong, approach.
Yeah.
We are basically building a ceiling made entirely of the model's own comprehension limits.
Exactly.
Well, thank you for tuning in to this deep dive on AI Paper Slap. We will see you on the next one.